Tesla earnings Q4 discussion and discussing an event about automated chip design. We decided to bundle those two events in one episode because I think they're both obviously warrant their own episode, but because the Tesla earnings call wasn't very fact intensive. It was more of a outlook for the next couple of years, and I think therefore we can probably keep it at a high level. And then the other topic is the same thing. We're not going to go into the nitty gritty of the engineering details, but discuss it more at a high level. So let's start with Tesla. I think the main three things we want to take away from the Tesla call is that there is enough potential here for the stock to stay elevated because we have AI coming through FSD and through Optimus. One of the hard facts was the announcement that we're going to have unsupervised FSD soon, and therefore paid robotaxi services. I think generally the business is actually not in the best shape in terms of growth and competitive forces. For example, we have a decline in the US and we have a decline in Europe. Now, whether that is because of brand image or because of other factors, it's a little bit hard to gauge that. Our conjecture is that we're looking at a convolution of situations. One is certainly some brand imaging because of Elon Musk's involvement in politics. So we have a lot of the environmental left-wing type buyers who stay away. But then we also have the other side, which is more people buying Teslas that maybe weren't exactly interested politically and now are interested. I think more importantly, I think that the company has to deal with a sluggish car market globally and an oversupply and hard competitive pressure in China. We're doing well in China, but I think the Chinese market is certainly a risk factor in terms of competition. So that's just something we want to keep in mind. I think the third thing is the potential of AI, and I think we want to discuss this a little bit more detail. Ashok gave a few interesting comments on the AI side of things. He spoke about the scaling of the model, and for example, he spoke about autoregressive transformers. So that's, to me, that is news. I wasn't aware that Tesla is actually using these modern models fully in their stack. So clearly they are. They're also working on semantics, for example, compositional reasoning. So it's not just a classification problem anymore. We have point clouds and trying to classify whether a pedestrian is there or not, and then the car acting accordingly based on end-to-end learning. But we also have semantics involved here, so we want to understand a little bit more what's happening in the actual scene, and therefore we can make decisions. What's important is that Tesla is building large training clusters for those reasons. So they're building large data sets. They have a modular model, so they can add data scenarios and train the model based on that. Now, there is a little bit of an issue with the hardware side, and Ashok spoke about this. We have longer context windows and memory issues, particularly with hardware 3, and I think that's part of the problem that we have right now with we have a hardware 3 Model Y that is running on V12.6, and there's some issues there with speed management. I think it's potentially due to the length of the context window and the lack of memory in hardware 3, which makes it just, the car is basically becoming very slow in thinking and therefore slows down. That's our conjecture. I think it remains to be seen what happens there. It's not a big issue for the company, hardware 3 people. I mean, we are affected by it, but the bulk of people have hardware 4 and are not affected by this particular issue. But what's more interesting here, I think, from a technological perspective is what does it mean, long context window? Long context window is the idea that you don't make decisions, so the robot doesn't make decisions, sort of step by step. The robot has the ability to take in a longer sequence. For example, it's driving towards a construction site, and then it sees some people playing maybe badminton next to the construction site, and there's a shadow, and over time, time being, let's say, you give it a few seconds, so the context window goes up maybe to 5-10 seconds. The model has emergent intelligence here, understands what's going on, understands the shadows, understands the people playing badminton are not actually, construction workers and things like that. I think that's the idea, and that is doable. It's been shown in various academic studies and conferences, and Europe has spoken about this. So there's a lot of context here that we think Tesla is soaking up. I think what's really interesting from our perspective here at Orange Capital Partners is the congruence between what we're seeing in the academic world and what actually Tesla is doing. So that's really very encouraging and very positive, and I think that gives us the confidence that this idea that Tesla could become a multi-trillion-dollar company actually has legs. The same applies to the Optimus robot. Musk was talking about this a lot. For us, this is a very interesting situation. We've spoken about this before because of transfer learning, so the ability to do compositional reasoning and having longer context windows, understanding semantics of scenes. All of these things transfer perfectly fine into robotics. That's exactly what robots need to do. So that's why we think that Tesla has a huge leg up. They also spoke about the hardware issues and the supply chain issues of the robotics in the robotics business. That is also something that Tesla is solving now. We don't know whether the Chinese supply chain is better, and we don't know what the competition is in China as far as Optimus is concerned. That's certainly one of the questions we have for our quarterly IR call. So we'd like to know what's the competition in humanoid robots in China, and we would like to know also what's actually the competition in FSD. What is the situation in China? Who is offering what? I mean, now with all the DeepSeek craze, I think that is a legitimate question. So now let's jump to the second topic, and that is automated chip design, a presentation we attended today here at Stanford. Links in the show notes. It's a professor from UCLA. I think that is a really interesting topic because it brings up two related areas. One is ML, so machine learning as a general problem, and then chip design as an application of machine learning. And I think like any other topic, we have when we apply machine learning to a domain, we always have to sort of be conscious about, okay, not every domain is the same, and not every machine learning technique is the same, and not every machine learning technique lends itself to every domain. Now, that is not exactly what OpenAI is saying. OpenAI is saying, no, that's actually not true. All we need is lots and lots of data on general algorithms, and then we can sort of use transformer architecture to generate intelligence out of the data. Now, that might be possible for large data sets, but in terms of chip design, we don't have large data sets. So what was interesting about this presentation was actually you really when you start thinking about the problem of chip design and then you apply machine learning to it, you learn a lot about what actually machine learning does. For example, the data problem, right? What exactly are we trying to solve? Now let's step back a little bit and think about what does actually chip design do. Chip design is the design of circuits so they can execute a certain task. So you want to write a program, and that program needs to be translated on hardware and actually executed. So that's in a very simple way what chip design does. So we have, the CPU is the famous chip that is sequential and therefore can be as general as possible and do almost any kind of task. And then we have maybe more special tasks. For example, the most advanced tasks today are dot products and variances and matrix multiplications, because that is very important for AI workloads. So let's think about this. Now, the question of chip design is, okay, how can we design chips that can do more, execute, let's say, a matrix multiplication? And the question when it comes to automate the chip design is, okay, can we automate the process of finding the optimal design choice? Design choices in chip design are, for example, parallelism, branching, things like that. Now, I've taken some computer architecture courses, but these are things that are, in basic computer architecture 101, you learn there are certain design choices that you have. So things that the chip can do, or counterfactuals. It can do this or it can do that. That's what a design choice actually means. And when it comes to automated chip design, it just means that maybe instead of having a human artistically exploring potential solutions, so we can have maybe at this branch we have some parallelism, but at this branch we do sequentialism, because given the tasks we might have more sequential dependencies here, and in here we don't, and things like that. So that's kind of like a human. It's a little bit of an art. And the beauty of automated chip design is that you can kind of optimize this. And then I like the sort of Sergey Levin approach towards AI in general, which is we have these two big branches of AI. One is the let's call it the transformer architecture, which is, okay, we have a compression of knowledge, which is represented in latent space in a sort of vector database. Knowledge being, okay, what is, let's say, what all possible states that a chip can have are represented in vector space, and then we have, let's say, some attention mechanism that connects all these specific modules in an attention mechanism kind of way, and then we can infer that certain things belong together. So, like I just said, for example, we could have an emergent intelligence which realizes that a certain task with dependencies cannot be parallelized, or that maybe the dependencies can be put in a buffer, and then you can parallelize for a while, and then you use sequentialism to put the dependencies together. So those are the kinds of things that sort of a transformer architecture could capture. And then we have the other side, which is the reinforcement learning, which is that given all the possible variations of potential combinations of solutions, what's the optimal path? Okay, and that is usually done through reinforcement learning. Now, the problem with reinforcement learning in general is reward functions and reward steps, right? So if we have, like in most cases in chip design, or we have a problem, which is that we probably will not know whether we have a good design or a bad design until the whole thing is designed, and then we execute programs on it. So reinforcement learning works best when we have intermediate steps that we can evaluate. And this is one of the problems that I've noticed in the presentation that came up, that is not very well organized in the chip design space. So we have these sparse reward functions, if you will, to use a technical term. So we only know after everything is said and done whether that is a good design or a bad design. The good news is that we're not talking here about absolute measures. We're not talking about creating the Mona Lisa of chip design. All we need is sort of in an A/B testing mode. We just need A to be better than B. And once A is better than B, we can add C. And if C is better than B, then C is also better than A, and so on and so forth. So that's kind of the situation that we live in right now. I think for us here at Orange Capital Partners, these are interesting presentations for a couple of reasons. One is this is really important business stuff. The gentleman that has been presenting has sold companies to Synopsys, so these are potentially even companies that we might invest in. But that's a concrete upside of dealing with this. But I think what's also interesting is the more general aspect of AI and chip design and automated chip design, and that is the idea that we have more and better and faster and more iteration in chip design, which will lead to better compute, more applications, and more suitable applications for compute. And that is, for example, something that Tesla is working on with Optimus and with FSD, with the inference engine on both of these projects. You need special chips. You can, or let me rephrase this, you can solve problems, AI problems and algorithmic problems also by having more suitable chips for the particular problem. So I guess what we're saying is that that the world of AI and the world of compute in general, it's not a top-down world where we just simply we have a fixed sort of hardware and now we have to optimize the software on top of it. It is a fluid world where we can optimize the hardware for the software, but we can also optimize software for the given hardware, and we can maybe even invent some hardware that can then enable us to do software that we weren't able to do before. I mean, that's partly what happened with AI. The reason AI broke through with ImageNet and then later on with ChatGPT was because the hardware side made huge advancements in parallelism. Now, to summarize the chip design side, I think in the end, everything that we do in AI is driven or is predicated on efficient applications of parallelism. Parallelism in all kinds of ways, and that's also, by the way, what Ashok said. So I think we're still in the mantra of parallelism is all you need. The more parallelism you can get, the better your AI models will be, the faster you will iterate, the better you will have solutions. Because what you need is, you need to try something and then very fast find out if you're on the right path. And the best way to do that is to have a lot of parallelism and also a lot of sort of sub goals and evals that you can benchmark yourself against. As far as Tesla is concerned, like we said, the earnings call was very inspirational, very optimistic, made us feel good. There's not a lot of tangible results right now that justify a $400 stock, but that's okay. Tesla has always been that kind of company, and it's actually remarkable how much credit the market is giving Tesla, and how much the company is benefiting from its ability to deliver and inspire at the same time. Thank you.